So far, we have learned various formal representations for regular languages, and they are deterministic finite state automata DFA, non-deterministic finite state automata NFA, NFAs with epsilon transitions, regular grammar, regular expressions, and Michael-Nero relations. And these six representations are sufficient conditions for regularity, meaning given a language, if we can find any one of these six representations for the given language, then we can conclude that the language is regular. And that is why we can say the existence of any of these six representations is enough to conclude that the language is regular. And we also have seen two necessary conditions for regularity. A condition is necessary means a regular language must satisfy the condition. And the first necessary condition that we have seen is pumping lemma condition. And we formulated a game which can be played to prove non-regularity. So by proving that a given language is not satisfying the pumping lemma condition, because the pumping lemma condition is necessary, we can conclude that the given language is non-regular. And the other necessary condition that we have seen is from the Michael-Nero theorem, and we show that a language L is regular if and only if the canonical equivalence relation for the given language is having finitely many equivalence classes. So this is giving us a necessary and sufficient condition for regularity. And this is the only condition that we learn which is both necessary and sufficient for regularity. So given a language, we can just find the number of equivalence classes induced by the canonical equivalence relation for the given language. If there are infinitely many equivalence classes, then the language is non-regular, and if there are only finitely many equivalence classes induced by the canonical equivalence relation for the language, then the language is regular. So we can see whether the language is regular or not by looking at this canonical equivalence relation. And that is what we have learned so far. And today we are going to see what will happen when we enhance the power of a DFA. We know that certain languages like a to the power n, b to the power n, where n is any natural number, or a to the power p, where p is prime, or a to the power n factorial, all these languages are non-regular. A deterministic finite state automata is not existing for any of these languages. So there is some limitations with the power of DFAs. Now the question is, if we enhance the power of a DFA, can we manage it to recognize these languages? And that is the question. And today we are going to discuss an enhanced form of a DFA which is named as two-way DFAs. So before we discuss two-way finite automata, let us recollect how a deterministic finite state automaton works on a given input. Here is an example deterministic finite state automaton for the language odd number of A's. That is, given an input string like this, the automaton should accept if there are odd number of A's. And this is the first or second example DFA that we discussed. Hope you remember it, and it would be nice if you can remember the structure of this automaton, because later in this lecture we may need to use it. This is E. The state E stands for even number of A's, and if you have already even number of A's, one more A means odd number of A's, and if you are here, one more A means even number of A's. And number of B's is not going to affect you, and that is why B is taking you back to the same state. So given this input, how the automaton is going to process the input, and that is what is called the computation of the automaton. You know that the computation must begin with the start state of the automaton, that is E. So you start with the initial state of the automaton, you are here, and now you read off the first symbol and you make this transition, that is the first transition, you are coming to the state O, and from O you read the symbol B. From O the B transition is here and you are coming back to O again, and the next input symbol is A, process it, and you are now getting into the state E, and from E you want to process B, you are coming back to E itself, and now the last symbol, which is A, which is this transition, taking you to O again. And in this case, the processing or the computation terminates in a final state, and hence the input is accepted. So this is how the computation progresses in the case of a deterministic finite state automaton. Now you can see that the input string is processed from left to right and is accepted if the computation ends in a final state when it finishes reading the input. And in a DFA, the read head of the automaton can move only to the right. So if it is here in pointing to the symbol B, in the next state it must be pointing to this cell with this A as input, and that is a finite state automaton. And now we are going to relax this restriction. Suppose we allow the read head to move either to the right or to the left, then we are going to get a machine which is a two-way DFA. A two-way DFA, and structurally same as a DFA, but we are allowing this machine to move its read head either to the right or to the left, and that is the only enhancement that we are going to give to obtain a two-way DFA from a DFA. Two-way in the sense it can move either to the right or to the left. So in this figure, you know that you are in state P and your input symbol is B. So what is the transition? In a DFA you want to say what is the next state, but in a two-way DFA you also want to say in which direction you want to move your read head, either to the right or to the left. Here you say that you move to the right. So if you move to the right, what will happen? The next state is Q, and you change your control unit to the state Q and you move to the right. This is what is going to happen. And you now consider the other possibility. You are here and the transition is this. Change your state to Q and then you make a left move. So what will happen? Now it's a left move. So you are moving to the left and changing your state to Q. So there is a typo, it must be Q. Sorry for the typing mistake. And so what we'll show is that the machine can make many rounds of scans on the input string by moving back and forth on the input string. What I mean is that starting from the left, if you want, you can go all the way to the right. So make only right movement if you want to do this. I am making all the right moves until I reach into the rightmost symbol, and not that in this case, unlike in DFAs, I am delimiting my input with a left hand marker and a right hand marker. Because I can move right or left, I want to have these delimiters. Okay, so what I did is I made a round of right moves, and then if you want you can make a round of left moves. You reach back to the leftmost symbol, that is a left hand marker, and you can repeat it any number of times. Doesn't matter whether you turn to the left from the rightmost symbol or from a middle cell, that you can decide. Maybe you can say that I will make 3 right moves and then 2 left moves, then 1 right move. Likewise, you can do any number of scans in the input tape by moving right and left. And how many times you want to move to the right or left, that you can decide. And that is this machine. And now the question is, then what is acceptance? And here the acceptance is also different. The acceptance is defined by a unique state known as the accept state. So the automaton, that is a two-way DFA, can accept a string by entering a special state known as state T. T is a special state known as the accept state. Once it gets into T, it will stay in T itself forever, and that is the accept state. Similarly, you can have reject state. So in order to accept, the automaton must enter the state T, and in order to reject, the automaton must come into the state R, and that is the acceptance and rejectance in case of a two-way DFA. And the differences are, the read head can be moved either to the left or to the right, and final states are not there, but there is a special state, namely T, which is called the accept state, and another special state, namely R, which is the reject state. And also, the right movement is not allowed if you are already in the rightmost symbol where the right end marker is placed. And the left movement is not allowed if you are already in the cell which is storing the left end marker. And these are restrictions. Later we can formally define it, and I think now we can move forward and see an example. And suppose you want to have a two-way DFA for this language. What is a language? The language is a set of strings over the alphabet set ABC, such that the number of A's in the input string is even and number of C's in the input string is odd. Suppose this is what we are going to look at. We don't mind how many B's are there, but we have to check the number of A's and number of C's. And number of A's is required to be even and number of C's is required to be odd, and that is the requirement. Now, suppose you are given with this kind of an input. Left hand marker, right hand marker is there. You are originally at the first cell, and if you look at this, there are only two A's, so even number of A's, and one C, odd number of C's. So this is a possible input to be accepted. Now the question is, how will you design the 2DFA? That is, you can move to the right or left any number of times you can do that, and how will you design? So here is one solution. First is, you do a left to right scan in the input to check whether the number of A's is even. So when you move to the right in this scan, you don't have to bother about B and C's. You just look at your A's and see how many A's are there. And then after, what you can do, you make a left to right scan, and in that scan you check the number of C's. That is what you can do. Make a left to right scan and see whether the number of A's is even or not. And then after that, you make a right to left scan, and in that round you look at the number of C's. And that is what you can do. And start with maybe this is the automaton to make the right scan. You see that all these marked like, if you are in Q0, if A is the input symbol, you move your read head to the right and change your state to Q1. That is the representation. Okay. And so this is represented by two symbols separated by the forward slash, and the first symbol is the input symbol, and the other symbol represents the direction of move, either to the right or to the left. And here all right moves, and this is the first step. You make all the moves to the right, whatever it is, and while you are making the move, you should see whether the number of A's is even or odd. If you are in this state, that means the number of A's is even, and if you are in this state, that means the number of A's is odd. So only for the input symbol A you are making a state change, otherwise you are retaining your state. Initially you have to start with the left hand marker, and later we can execute the input with this machine. Okay, so the first step is over, and when you finish scanning from the left to right, you know that there are two A's, and so you will come into the state Q0 because two A's only. And what is the next input symbol? It is the right hand marker, and what you have to do is when you process the right hand marker, now you have to do a round of left moves. So you are moving to another state on the right hand marker, and where you started moving to the left. After the right hand marker I am moving to the left, and here what I have to do is I have to check the number of C's, and this is how I can check it. So here what I am doing is very similar structure. I am checking the number of C's in it. Okay, so Q2 means the number of C's is even, and Q3 means the number of C's is odd, which is not a difficult logic because you already know it. So all left moves, and I am checking the number of C's whether it is even or odd. And see, in this case, if I reach here, only one C is there, so it is odd. I will be ending up in this state. So I am in Q3, and I am going to process the left hand marker. That means now there are even number of A's and odd number of C's, so I can accept. So when I reach into the left hand marker, I can say that if it is a left hand marker, then from there move right and enter the accept state, and that is what I can do. And now suppose when I make the first round of move, this is a different input. Suppose there are only odd number of A's, in this case it is 1, then I will be ending up in this state when I finish the first round. Then what do you have to do? Now the input is not satisfying the condition. In the first round itself you identified that the input is not satisfying the required condition. So no need to do any more processing. You can decide to move into the reject state. So in this case, for this right hand marker, you move to the reject state. And the other possibility is so the right move is okay because two A's are there. Suppose you move to the left, you found that there are even number of C's, but we need odd. So even number of C's means you will be in this state, and you will hit this situation where the next symbol is the left hand marker. That means there are only even number of C's is even. In that case also you have to move to the reject state. Okay, that's automaton. And now the design is not completed because it has to be a deterministic automaton, and all the moves must be defined, and the moves are not defined for T and R, and which is always this kind of a move. Once you come into T, you cannot move out to any other state. What you do is for all the symbols, you move your read head all the way to the right. When you reach into right, you just move left, and you will stay here in these two symbols forever, and that is what you do in a 2 DFA. Similarly, you do it for the reject state. You move all the way to the right and you stay there, and that is this machine. And now you can see what is happening. You try to execute it, and before that a 2 DFA cannot make a right move from the right hand marker or a left move from the left hand marker. These restrictions are there. And also, once a 2 DFA gets into either the state T or R, it stays in that state forever and moves all the way to the right. Moves the right head, read head all the way to the right. So these states T and R are said to be sync states because once the 2 DFA gets into any one of these states, it stays back in that state forever. And so this is an example DFA, and now you see the computation on this input. You start with the start state, and you are here. Now you read the left hand marker and you take, because this is the left hand marker, transition for left hand marker is there, and you come back to Q0 itself. And what is the next input? It's B. And from here the B transition is again this, because this is the B transition. You're coming back to Q0 again. Next is A, and A is taking you to Q1, and next symbol is C. From here the C transition is again coming back, and now the last symbol which is A, and which is taking you back to Q0. And you are in Q0, you are getting the right hand marker. What is the transition from Q0 for right hand marker? You are moving down. And now you are here, you started moving to the left. And what is the next symbol? It is A. And what is the transition for A? This is the transition, you are moving left, and this is the transition. And next symbol is C. From here the C transition is taking you to Q3. And then next is A. A is this self loop coming back to Q3. And next is a B. And where is the B? B transition is again taking you back to Q3 itself. And now you are here in Q3. And in Q3 you are now going to process the left hand marker, and here is the transition which is taking you to the accept state. And the moment you reach into T, you know that you accept. So unlike in DFA, here there is no need to even finish reading the input. The moment you get into T, that means the 2 DFA is accepting the input. After that, it's clear that it will move all the way to the right, that's fine. But in between also it can decide to accept, or it can decide to reject. And that is the input. And maybe for this input, it's true that there are 2 A's, so even number of A's, and 1 C, that is odd number of C's, so it is accepted, that's correct. But you can verify that this is a precise design. That is, the input is accepted if and only if there are even number of A's and odd number of C's. If you want, you can use principle of mathematical induction to prove the soundness and completeness of this construction. Let us look at one more example. So this is an accepted case. Next DFA is 2 DFA is for all the strings ending in B. AB is the alphabet set. So how can you design? So given this kind of an input, maybe this is ending in B, you can accept. So how can you do it? The idea is, first move all the way to the right. Okay, you don't have to look at what is it. You make all the move to the right, and then what you do, you turn to the left. So turn to the left, and then you see that the next symbol from the right side is a B. That is what you can do. So you go all the way to the right, then make a left turn, and then observe that what you are having as the first symbol from the right is a B. So that is the idea. So start designing it. You start with the start state, and what you have to do, you make right movement until you reach into the right symbol. This is what you do. Okay, whether it is a left symbol or A or B, you move to the right. Finally you get into this situation where you are getting the right hand marker, where what you want to do, you want to turn to the left. For that, what you do is, because you are changing your mode of operation, you are going to do a left turn. I make a state change, and I am in Q1. And in Q1, to accept, I know that if the last symbol is a B, next I am going to see a B. If I am seeing a B, I can go to the final state. Sorry, not final state, I am wrong, to the accept state. And that's what I can do. And suppose instead you had A here, what you have to do? A means you cannot accept it, the last symbol is A. So you have to move to a reject state. And another possibility is, suppose the input is null string, then what is the symbols? What are the symbols on the tape? The left hand marker and the right hand marker, successive symbols. In that case, this will happen. And so that is this transition also handles that case where the input string is empty. Then this will happen. Okay, now you know that you have to complete the transitions by defining self loop for T and R, and that is the machine. So now we have 2 example machines, and I think this is enough for us to formally define what is a 2 DFA. So we're going to formally define it and consider the last example to recall what are all the components of the definition of a two-way DFA. A 2 DFA over an alphabet set sigma is a subtuple A, where what is Q? Q is the finite set of states. All the states are going to become Q, and the next is the left hand marker. This is the left hand marker. Then the right hand marker. These are special symbols, not a part of the alphabet set, but special symbols on the tape. That is extra. And then the transitions. These are all the transitions here. And if you carefully look at it, how a transition is defined, a transition is defined, for example, this transition, if you look at it, it is defined from a state for an input symbol or for the left hand marker or right hand marker. These are the possibilities. Either it is for a symbol or for a left hand marker or right hand marker, and this is how you mathematically write it, from a state for an input symbol or for left hand or right hand marker. What you say, you move to a state, and you also say what is your direction of move for the read head, left or right. So that is the definition of the transition function. And now the next component is small s, which is an element of Q and which is the start state, in this case Q0. And next is T, which is an element of Q known as the accept state. And finally R, which is this should be R. R is an element of Q, and R is not equal to T. These two must be different states, and which is called the reject state. And with this, we are finishing the definition, and I'm giving you two assignment questions. You design two DFAs for the following languages. The first is set of all strings over AB where the number of A's is a multiple of 3 and number of B's is a multiple of 2. And the second language is the set of all strings over AB where the second last symbol is a B. So today we have seen a new type of finite automata, which is a two-way finite automata, where the read head can move either to the left or to the right. And if you want, you can scan your input any number of times. And the automata accepts by entering a special state, namely T, and rejects by entering a special state, namely R. And once you get into either T or R, you cannot move out of the state T or R. And you are not allowed to move to the right from the right hand marker, and you are not allowed to move to the left from the left hand marker. And that is a 2 DFA. Please solve the assignment questions, and in the next class we can see whether 2 DFAs are more powerful than DFAs for accepting languages. Thank you.